I've often wondered that when I have viewed Venus, she always appeared to me all over equally lucid. I cannot say I observed so much as a spot in her. Is not all that light we see reflected from an atmosphere surrounding Venus? Oh!
The 17th century Dutch scientist Christiaan Huygens had identified the feature which makes Venus so bright that it can often be seen even today as a star-like object in the twilight sky. But the dense reflective cloud cover which makes Venus so brilliant was to keep its surface shrouded in mystery for hundreds of years, to the frustration of generations of scientists. This program is about the technological quest which at last succeeded in revealing the long hidden surface of Venus, and the question which scientists can now begin to answer. Could Venus, beneath its clouds, be a geological twin of Earth?
In the late 70s, we essentially knew nothing about the surface of the planet because of the cloud cover. And the cloud never clears, so you can never photograph the surface of the planet. And that's fine if you're interested in clouds, but it makes it very difficult for people like us who are interested in looking at the surface features of the planet.
For today's scientists, Venus is of particular interest. It is Earth's closest planetary neighbor and is similar in size and mass. So perhaps it has had a similar geological history. In the early 1960s, hope emerged that the surface of Venus might be revealed by new technology. Space travel was turning from dream into reality, and since the Venusian surface could not be seen from the Earth, why not go there direct? Venus was made a target for many of the early missions in the 1960s. Not all of them were successful. A series of Soviet missions were bent on breaching the atmosphere of Venus. The probes of the late 1960s made atmospheric measurements in descent before succumbing to intense heat and pressure at the planet's surface. The atmosphere of Venus was found to be extremely dense and acidic, with a surface temperature of almost 500 degrees centigrade. Such a hostile surface is very different to the Earth. But that didn't mean Venus couldn't be geologically similar. Progressively more sophisticated Soviet probes at last succeeded in soft landing on Venus between 1972 and 1981, revealing its surface for the first time. In 1972, Venera 8 carried a camera as well as a device for making crude chemical analyses of surface material.
The Soviets sent various landers to Venus which were designed to come down through the atmosphere in a parachute and to withstand the very high pressure and temperature on the surface. And 3 of these scooped up a little bit of surface soil, and the amount they could analyze was really no bigger than the end of my little finger. And the composition they found from the surface was basaltic, essentially indistinguishable from the material which makes up the Earth's seafloor.
Later Venera landers were even able to take color television pictures close up to what could be basalt slabs on the planet's surface.
I've got a lump of basalt here. It's a piece of volcanic rock taken from the surface of the Earth, but in terms of its chemistry, it's pretty much what the surface of Venus appears to be made of. The trouble is we can't be sure that this is what the lander pictures are showing us. The slabs could be the broken surface of a basaltic lava flow like this, but they could also be pieces of sedimentary rock, or maybe just some kind of hardened crust formed on top of the soil.
So the pictures were ambiguous and the chemical analyses crude. with large uncertainties in the measurements. And the landers all went to the same part of the planet, so no one knows how representative the samples were. Imagine the impression a visitor would get of Earth by going to just one region. Technology had now brought scientists too close to be able to interpret geological features.
To really understand a planet, you need images covering large regions. Well, this applies to the Earth too. For example, there are large-scale fault features on the Tibet Plateau, and these were first noticed on images from cameras carried by satellites in Earth orbit. A technique's called remote sensing.
But how could remote sensing from orbit see through thick permanent cloud cover such as that surrounding Venus? In 1978, the American probe Pioneer 12 used a technique called radar altimetry. Radar can penetrate clouds, and the data gave the first map showing the topography of Venus. Radar altimetry works by sending a stream of microwave pulses from an orbiting spacecraft vertically down to the surface. By timing how long the echo takes to return, it is possible to work out the distance between the spacecraft and the ground. With enough points, a planet-wide map of surface heights can be assembled. This map of Venus is color-coded to show heights relative to a planetary average. Blue is used for the lowest areas, and green, yellow, and red for progressively higher ground. This makes Venus look much like the Earth, the blue areas resembling oceans, but the similarity is artificial. In fact, radar altimetry pointed out an important difference between Earth and Venus. Plotting altimetry data for Venus, the surface heights cluster around a single value. Plotting similar data for Earth shows two distinct peaks. So while on Venus there does not appear to be a fundamental distinction between high and low areas, on Earth there is.
The Earth's got two distinct types of crust. There's basaltic crust, which forms the ocean floor, and basalt's a dense rock, and the oceanic crust is typically several kilometres below sea level. On the other hand, continental crust is made of less dense rock types and is a thicker crust, and that's why the continents are mostly dry land.
The observation that Venus does not show this bimodal range of surface heights is persuasive evidence that it does not have two separate types of crust like the Earth. So what is the crust of Venus like? While altimetric maps give a height distribution, their resolution is too coarse to give a good impression of the surface. Another technique had to be found for scientists to see large-scale features. Preparations were made to use an imaging radar to map Venus. Two Soviet Venera probes were the first to attempt this in 1983. An orbiting spacecraft sends a fan of radar signals obliquely down to the surface. Much of the energy will be reflected away and lost, but so long as the surface is not glassy smooth, some echoes will be returned. To maximize detail, radar images were collected using a technique called synthetic aperture radar. By drawing data from different positions, computers can interpret the information as if from a single imaginary antenna much larger than the actual craft. The Venera radar images revealed the first widespread views of the Venusian surface. Represented in this form, they look very much like a black and white photograph.
Not very high resolution photographs. Their resolution's only about 2 kilometers of a lot of the northern hemisphere. What was completely unexpected on the Soviet images were these very large circular features with radiuses of 100 up to about 500 kilometers. And we really had no idea of what these were at all. And what we hoped was that when we got the high-resolution Magellan data, which looked as if it was going to be wonderful, we'd be able to sort out what these things were and whether we were dealing with an internal process or whether we were dealing with essentially meteorites hitting the planet.
Hopes for answers to these questions rested on an American space mission called Magellan. Planned since the 1970s, It was to carry out better radar altimetry than Pioneer and higher resolution radar imaging than Venera. What's more, it would do it across the whole of Venus.
Moving into the orbiter now. He has been standing there waiting his turn. 11, 10, we have a go for main engine start. 7, 6, we have main engine start. 0, and liftoff. A new era for planetary science begins as Atlantis clears the tower.
The mission was long delayed. Cost constraints meant it had to be redesigned, and its deployment was set back by the interruption in the Space Shuttle program after Challenger exploded in 1986. Magellan was eventually launched in May 1989 and went into orbit around Venus in August the following year. It was the start of a 3.5-year mapping program. From the outset, the information received from Magellan provided stunning pictures of Venus. By combining altimetric data with Magellan's detailed radar images, three-dimensional models can be created in computers with color added to match the Venera lander pictures. 300 years after Christiaan Huygens, the Venusian surface had at last been stripped of its atmosphere, its rocks laid bare. But stunning though these flight sequences are, they are deceptive. Venus is really much flatter than this. The vertical scale has been exaggerated to make features show up more clearly. Scientists like Dan Mackenzie are much more interested in the images themselves.
The mapping itself started along this line here. And you can see some of the first things that we saw were these small circular features down here, which on the Soviet data we couldn't tell what they were. But on this one it's clear. On the Magellan data you can see clearly the ejecta associated with these little impact craters. If we go further to the northeast, up here, you can see some of the other types of features that we could see on the Soviet data, like this one and this one here. And these are not caused by impact. These are some sort of internal volcanic process which has produced them. And they come in all sizes. The ones that we could see very clearly on the Soviet data, right, like this one over here, which is much bigger. And this, what we can now see, is that there are essentially two different types of circular features. Ones which are produced by impact, and other ones like these, right, which are some internal process.
At last, features could be identified on imaging radar which looked very much like some seen on Earth. Comparisons were further strengthened when topographic maps from Magellan's improved radar altimeter were considered.
In this part of the planet, we can see things which we think we can recognize. And I remember very clearly when I first understood this. I went on a visit to Peter Ford at MIT, and he had topographic maps of this area here. And the asymmetry and the shapes and the scale is just like the Earth. And I remember very clearly going there and saying, oh gosh, it looks just like the East Indies.
Dan arrived just as we'd finished processing our first high-quality data from the Magellan altimeter. He was particularly interested in looking at the cross-sections of the giant chasms which cut through the equatorial regions of Venus. For instance, this one named Aphrodite. He noticed many points of similarity to the great ocean trenches of Earth, such as those that lie between New Guinea and Fiji.
And this was really not what people believed before. They thought this was an area of extension of spreading ridges. And it came really as a surprise to people, right, when it was so clear from the Magellan data that you could see these features. And everybody since then has really jumped on the bandwagon.
So although the radar altimetry is much cruder than the images, it provides crucial evidence for the crustal stresses that have produced these features such as chasms. And what's more, those forces must still be at work. Otherwise, the steep slopes more than 25 degrees that we see in many of the chasms would very soon have slumped away, given the very high temperature of the Venus surface.
We can get some clues to the mechanisms which might be at work on Venus by looking at Earth. On Earth, trenches are found where one tectonic plate is drawn down under another. Usually there are volcanoes formed on the overriding plate. If the Magellan images show trenches on Venus, then could the same mechanism be responsible?
Evidence for trenches on Venus suggests that we found another planet with plate tectonics, even though the crust of Venus appears to be a single type, not divided into oceanic and continental crust like the Earth. But if Venus does have plate tectonics, there ought to be some other signs of it too.
Once we'd found what we thought were trenches on the planet, it seemed obvious to look for other features which were where you make new surface areas, spreading ridges and transform faults. And the only area of the planet where we found good evidence of these things is within this large circular feature here called Artemis. And down in the southern part, there are features which I think were produced by spreading ridges and by transform faults. Whether they're still active or not, we can't tell.
Artemis is a wide ring of dramatic land features in the southern hemisphere of Venus. The ring is about 2,000 kilometers across, a little larger than France. It is the comparatively flat ground within the ring that Dan Mackenzie believes has been caused by spreading ridges and transform faults. On Earth, spreading ridges form where new material is added to the plates to compensate for that destroyed at the trenches. Transform faults occur where individual plates slide past each other. So if Mackenzie is right in interpreting the features of Artemis as trenches, spreading ridges and transform faults, then the evidence all adds up to plate tectonics on Venus. Or does it?
The problem is that whatever these features are, they've only been seen in the Artemis region. Now, if Venus is an active planet, and this seems inevitable, then deformation and recycling of the crust ought to be going on in lots of other places as well.
It is the mysterious circular features seen by both the Venera and Magellan missions which could provide the key to answering this problem. It's possible that these circular features lie over sites where hot material is welling upwards within the Venus mantle. The concentric structure and rifting within the circular features is consistent with a thinning and stretching of the Venusian crust. While on Earth, heat is removed from the interior of the planet by the creation of hot new crust and the subduction of cold crust, Venus might have a crust too thin to mobilize extensive plates of material. Instead, the convecting mantle might cause regional pileups of material in a pliable crust. So is this the mechanism behind the mysterious circular features seen on Venus? Again, it is impossible to be sure without more information. Even quite fundamental problems about the interior of Venus still remain unsolved.
Quite apart from the problem of understanding the internal origin of these big circular structures, we already have a major problem in understanding what we now see. And this really is connected with the way in which Venus loses its heat.
The trouble is, we don't really understand how Venus loses its heat. Now, it's made of essentially the same stuff as the Earth, and it's the same size. So the rate of heating of the interior by radioactive decay should be pretty much the same as the Earth, and so Venus should be losing heat at the same rate. But when we look at the evidence on Venus, this doesn't seem to be what we see.
There are three ways in which the heat generated inside a planet can be transported to the surface to be radiated away: by conduction, through volcanoes, and by plate recycling. Different bodies lose heat by these mechanisms in different proportions. Inactive bodies like Mars and the Moon lose almost all their heat by conduction. But on Earth, by far the most important mechanism is heat loss by plate recycling. The cold edges of plates sinking beneath trenches and the addition of hot material at the edges of plates along spreading ridges. So we might expect an active Venus with similar features to lie in a similar region of the triangle. But the Magellan images suggest that this is in fact unlikely.
Now the problem is that the number of impact craters on Venus suggests that its surface is on average about 10 times older than the average age of the oceanic crust on the Earth. That's 500 million years as opposed to 50 million years. Now if the Earth is getting most of its heat out by plate recycling, and we're pretty sure about that, then how does Venus get the same amount of heat out if its surface is only being renewed at a tenth the rate? That's something we can't really answer at the moment.
Gravity surveys of the planet might help to clear up some of the mystery. But even so, Dan Mackenzie aspires towards rather more ambitious plans for the future, aimed at stripping away not the atmosphere of Venus, but the surface itself.
And what we really need is seismometers, which can record seismic waves as they pass through the planet to see what's actually happening and map the internal structure. And I think this is really going to be the only way of making further progress. And rather surprisingly, it's perfectly possible to put seismometers on the surface to record things in this way, provided you don't use solid-state electronics, but you use valves.
I cannot but think of our diverting labour in polishing and preparing such glasses, inventing new methods and engines, always pushing forward to still greater and greater things. And yet there remains much more to be investigated. I owe much to him who shall be able to supplement that which is here lacking to me in knowledge.